we were talking about the k generalized k-dV. That is this equation. And this is the initial data. K equal to 1 correspond to k-dV. K equal to 2 to the modified k-dV. These are integrable cases.
So integrable cases means what? Again, sorry.
That inverse scattering apply.
That inverse scattering apply. Okay. Oh, for k bigger than 3 and above?
No, well, there is no condition that tell you that this equation is integrable or is not integrable. There is something called Lax pairs and things like that. But, right, the only two that have been proved to be integrable are these two, plus another one that I will mention in that moment, but it's not pure power.
So the other one, we don't know yet.
Well, almost sure it's not. But it's not proof that say, theorem, the only power that the only integrable are this. That theorem, I don't know that. For any k integer, we have the traveling wave. If k is equal to 2 and 2, it's called soliton because they interact in an elastic way. Then qk with a speed c is equal to k plus 1, k plus 2, and I'm copying. Don't think that I know this by heart. We're going a square of k over 2
But wait, there was not a difference. I mean, for
no, it's the same one.
oh.
When k is equal to 1, you have the secant square. When k is equal to 2, you have the flat secant.
Okay, yes.
Okay. Okay. I think that's okay. That's then we saw that these interact elastic, and we studied the stability, but we want to study a different kind of solutions. And then there are some dispersive equations that possess some solution called breeders. And breeders are, let's make this definition, some solutions that are localized in space. That means that they decay very fast at infinity, and they are periodic in time. Okay? And which equation are known to have breeders? The modified k-dV and this equation. This equation is a little bit, it's kind of a combination of the k-dV with the modified k-dV with this parameter mu there.
Yeah, right.
And this is called the Gardner equation. And this equation, the k-dV and the modified k-dV are known to be complete integrable. And they are the only three that are known to be complete integrable that have to do with the k-dV.
Sorry, you say they are integral.
Yes, they can be solved by the inverse scattering method.
But they are not completely.
They are the only one that are known to be.
Known to be, right, I'm sorry.
Okay.
Okay.
Okay, then for the Gardner equation, okay, you have KdV is u dx of u modified. Gee, what did I do? Oh, okay. I'm sorry, I touched something. Okay. Okay, then we have the modified KdV, that is u squared dx of u, and we have the Gardner equation, that is u plus some parameter there, mu squared, that is a kind of combination of this.
It's kind of a superposition in a way, right?
Yeah, and these are integrable, and these are the only three that are known to be integrable, okay?
Yeah.
Okay, and then breather are very strange solutions. So you're not looking for a solution that is localized. Localized is, for example, the traveling wave is localized because decay. But the traveling wave is traveling. This want to be periodic in time. That means that you stay there. Okay. Okay, we will go to the formula, but let's see that there are some solutions that, some other equations that have breathers. For example, this equation is called the Sine-Gordon equation. It's also integrable and have solution of this form that is time periodic. See, the bottom that is has to do with this hyperbolic secant, have nothing to do with the time, and the time only appear cosine here. Then this gives you the decay. When you take the derivative here, they give you the decay, they give you the periodicity in time. Okay, and these are real solutions. If you don't care about real solution, then you can look, you have examples of systems that are not integrable that have breather solution. For example, suppose that we consider the nonlinear Schrodinger equation of this form.
So breather solutions are those that are
Periodic in time and
periodic in time
space.
and localized in space.
Yes, but they are real. We mentioned the KdV, the solution is real. The solution for the Sine-Gordon is also real. But if you put complex, then you have plenty more. For example, this NLS, right? This NLS equation with this sign have to be minus, then you want a solution of this form.
That's nonlinear Schrodinger, right?
That's nonlinear Schrodinger, and you want a solution of this form when this only depend of x is going to be a function that decay, and this give you the oscillation. Then if you substitute that there, then this bar phi has to satisfy this elliptic system, and then is proof that solution of this exists. They belong to some H1, they are positive, therefore you have solution of this form, that they are periodic and in time, localized in space. And this equation is only integrable when you are in dimension 1 and nonlinearity 3. But you have this kind of solution that is called a standing wave. They are not calling breather because they are complex, right?
But wait, but so n equal 1, alpha equal 3.
That is the only integrable system that among all this family, the only one known. But these solutions are not real. They call a standing wave. This is called the ground state, this part. Then this decay like, this is like hyperbolic secant. Decay very fast, and this part gives you the oscillation. But this is complex.
Yeah.
Okay.
And you cannot avoid the I. You cannot.
That is controversial, and that is okay. then look what we have. Remember that for the modified KdV is this one. The solution in this case, the traveling wave solution is this one. With a speed c is k-2, then it's some numbers, let's see. Okay. I think it's 3 hyperbolic secant of square root of c x. That means that the solution looks like this. Okay, and then the traveling wave really is this one. Okay, then this is a traveling wave. What we have here is the formula that Guadati deduced for the breather. Okay, now you have two parameters. You don't have one parameter, you have two parameters. Is the derivatives of the arcotangent. When you take the derivatives of the arcotangent, then the cosine hyperbolic stay there. And this is going to give you this hyperbolic secant that is exactly what you have here. But the sine part gives you oscillations. And this, you have these this parameter free. And if you fix this parameter here, gamma, to be 0, that means this part is 0, then you are totally localized in time. You are not moving the bump. This is the bump. And this is the part that gives you the periodicity in time. Then your solution is going to look like this. Your solution is going to look this is the hyperbolic secant. This is the hyperbolic secant. And you have the solution is something that look like this. And it's periodic in time. You're going to oscillate inside and is moved with this.
But something probably is very elementary, but I mean, you have the Q solution.
Yes.
You can prove, like when you take the derivative, you can prove that that satisfies the equation, right? And here, I mean, I'm still surprised you can get another type of solution.
Yes, this is another solution.
That has to be localized in space and period.
Okay, let's say, why do you think that this solution should exist? Okay. Okay, suppose one way to motivate will be this. Suppose that you put a traveling wave going like this. That for the KdV exists. But you have traveling wave like this. Negative traveling the opposite. Then if you put this one traveling wave to the right and the left traveling to the right, one in the left negative traveling to there, when they interact for a short time, they give you something like this.
Oh, I see.
But the issue is that they stay forever like this.
And
This is called a king. This is an anti-king. Or something like that. And when they interact, they look like this for a short period, and then they go by each other. Yeah.
Because of the elasticity.
Yeah. Okay. But this one, no. This one start like this and stay like this. Okay. Okay. Then, and also you have two parameters, not one, because the velocity. Then you can change the velocity, this parameter, to be positive or to be negative. Then you have this breather can be periodic or travel to the left or travel to the right. Politically very convenient, right? but let's define that breathers are periodic in time, localized in space.
Yes.
And for example, then you have to have this, if this constant is zero, this conservation, we know that this is the third conservation law, has to be zero for the breather.
Has to be zero.
Yes, you have a lot of, you don't have a lot of flexibility. You have a lot of things you have to satisfy to be a breather. It's very complicated to be a breather. Right? Okay, then we saw that we have breather in other equation. And then you can ask, the first question is, are the breathers stable in the sense that we already studied? The stability of the traveling wave. And the
Just
answer
for completeness, H1, H2 are
solar spaces.
Sobolev spaces.
Okay, H1 of R functions from R to R, such that F and, let's put Fj,
is in L2. Okay.
then for the modified KdV, Alejo and Munoz prove that they are stable in the sense that if you start close to a breather, your translation will be close to a breather at a later time. This is the same stability that you have to understand the solitron. And to do that, they prove that they need two parameters, and they need H2, and they prove that the breather satisfy this four-order equation. Remember that to deduce the traveling wave, we went to a second-order equation. They have four order because they need two parameters, and they need H2 because they have two parameters. Okay. Then the goal will be to show that, well, the good thing will be to show that there are a lot of breathers. But since this is very complicated to find, it's much easier to prove that there is no breather. Right? Then the goal is to show that for this equation, the generalized KdV, when you can power here or not, for this equation, you don't have breathers. Okay? And then we are going to use the notation that this is Hn, that you have n derivatives in L2, and you are in L2 with this
weight.
That means that you have enough decay. Okay? And the first thing that we proved with Munoz, like 2 or 3 years ago, I don't remember, we proved with Munoz was the following. Suppose that you have a non-trivial solution of this equation that is periodic in time with period omega. Then this has to be zero. Therefore, if you put the nonlinearity U squared, that is the KdV, you don't have a breather. If you put the nonlinearity U squared, that is k equal to 3, you don't have a breather. If you put any power that is even, you don't have a breather. And if you put a nonlinearity of this source, I mean, if you don't, this is a perturbation of the garden, you don't have a breather. Then you kill a lot of possibility of having breather, but with this trivial result. And this is very simple, This is the only proof that we will do because it's trivial. Okay.
Yeah,
And-
we like simple proof.
Yeah, and that is kind of interesting because when I heard Claudio proving the stability of the breather, I told him, this is an open question. You should prove that, you are the guy who should prove that the breather is only exists for the modified KdV and the Gardner, right? Well, after a few years, he sent me a proof, very complicated, that, and we will get there. But then we start to work, and then we did several theorems, and we modify and improve what he has done and make this very simple. Okay, we don't need this decay and this regularity. If we care, that's not, the only thing that you need is that X multiplied by this is L1. And the same result, the same proof, work for other equation for the
What is the H42R?
is that you have 4 derivatives and you decay like L2 with this power 4. That means that you have 4 derivatives and you are in L2 with this.
With that weight.
Okay. But you need only this. And this is that the same result applied to the Kamasa hole, to the internal long wave, to the Benjamin-Ono equation, all integrable. You can prove that none of them have breathers. Okay, I'm not going to write the Benjamin-Ono, the Kamasa hole, but that's okay. Okay, let's do the only proof that we are going to do, and this is the total proof. Okay, you take the equation, and you multiply this equation by X, and you integrate in a space. Then you can take the derivatives of psi here. You have X, U cubed here. You have X dx of this. If you integrate by parts, if you have enough decay, this is 0. If you integrate by part, this is equal to this. You don't have boundary term because you decay by part. Therefore, you have the derivatives of this function equal to this. Then you integrate in time, but you are assuming that you are periodic. Then if you integrate in time in the period, this quantity has to be equal to this quantity. Then therefore this is 0. Then this quantity has to be 0. That's the proof. Then you prove that if you have a solution that is time periodic, it has to satisfy this. In particular, the nonlinearity cannot be even. Then the KdV have not breather. Right? It's a very simple proof.
Just integration by parts.
Yes, like Vries used to say, if I can do it only with integration by parts, that's your technique, I know. Okay, then we can prove other things. For example, we can prove that if you take the Gardner equation and mu is positive, you have breather, but if mu is negative, you don't have a breather. And that is a little bit more complicated. That means the Gardner equation have breather when mu is positive, but not when mu is negative. Okay. Then another thing that you can prove is that you take any of this power when you don't know that you have the global existence is only known if you are small. Then suppose that you take the nonlinearity is the power k here, and you perturb this. This is a small perturbation near 0. Then you don't have breather solution that are small. This global existence only is guaranteed if you are small, but if you are small, you cannot have a breather. I mean that. Then if you put all this together, it seems that almost prove that the only power that have a breather is the modified KdV, k equal to 2. Why? I don't know. Besides fat. And then you can even be very precise and say, okay, how small you need to be in order to guarantee the issue. How small you have to be as small than this number. If you have exactly the power 4 here, and you don't have
Where
perturbation.
Q is the traveling wave. Oh, right, yes.
Yes. Q is Q4, in this case will be Q4, right? You can make it very precise. Okay, now this is something that it was the original proof after some modification, but that was the original proof that Claudio sent me. He proved the following. Suppose that you have an interval of time that grow with time. It grows like t to the power 1/2 to the right and to the left, and have a log in the bottom. Then if you have a solution that satisfies this, the H1 norm, that means the solution, the derivatives of the function in L2 and the function in L2 in this domain go to 0. Even that this domain is growing, this goes to 0. That means that you cannot have solution that is periodic. All solutions have to move to infinity. They have to move to infinity, which is not strange. Remember that if you are a soliton, you move with a speed proportional to t. You move faster than this. A soliton satisfies this, right? A soliton satisfies this because the soliton will move with a speed ct.
CT, right.
Right? Okay, then this condition is unpleasant because it's not clear what solutions stay there.
So
It's not
those
clear
are
even.
essentially bounded function that goes from R to L1 of R, right?
Yes, it's that the L1 norm of the solution in a space is globally bounded in time. The L2 norm is bounded globally, but the L1 norm is unknown that is global. Then this hypothesis was removed by Argenis Mendez, Muñoz, Pobletti, Pozo, and they even extend this interval that was t to the 1/2 to t to the 2/3, a little bit less than t to the 2/3. But this limit is not a limit, it's a limit inf. That means that there is a sequence of time that satisfies this. You remove this hypothesis, you are in a larger interval, but you don't have the limit. You have the limit in a sequence of time. Okay, that's the improvement that they got. Okay. What should be the solution? I mean, what should be the real? What should be the sharp result? It should be that if you move with any power less than 1 here, you should have this.
Less than 1.
Less than 1. If you move, because the traveling wave moves with a speed t, right? Then if you move less, it's like this. But this is if you accept something called the resolution conjecture, soliton resolution conjecture, that say that at the end of the day, all solutions at infinity behave like superposition of finitely many traveling wave plus some breather plus something that look linear and small.
So in this integral with the lim inf, that the power is 2/3.
Yes, better than 1/2.
Yeah, but you are not dividing by log of t.
Yeah, but the log is only take your epsilon, right, in the power.
Yeah, right.
And this is t is 2/3 minus. You don't reach.
At 2/3 minus. Okay.
Okay. Then, if you stick with this problem, you want to know. You know that suppose that forget about the H1. You know that the L2 norm is preserved, right? If you satisfy the KdV, then this quantity is exactly the quantity that you start with.
Yeah, it's preserved.
Then you want to say, okay, where is this L2 nor when t goes to infinity? Well, you are proving that this L2 nor moves to minus infinity or to plus infinity, right? You are moving that this L2 nor is not here, in at least in a sequence of time. Then Martel and Merle prove that if you give me a solution that is for the KdV, right, there exists a constant that depends on the nor of the initial data in H1, such that if you integrate the L2 nor, let's forget this part, the L2 nor for all the x larger than this, you have 0. That
So
means that
what is the meaning of that?
If this is 0, here you are C0t. At the time t, you don't have any L2 nor in this part.
Oh,
Think about that. If you have a traveling wave, where is the L2? It's moving with a speed,
see.
right? With some fixed speed. How big is the speed? It's a multiple of t.
Right.
If you put a multiple that is larger than the amplitude, then you kill.
You don't see anything.
You don't see anything. But of course, this is only for traveling wave. And the proof of this is very simple. It's very simple. It's almost the proof of the Cato smoothing effect. Right? And of course, then you go here and you say, well, but what about why you don't put L infinity here? The amplitude and the speed are related with the L infinity. Well, the problem is that only the L2 nor, the H1 nor, the H2 nor are preserved by this. Then the L infinity nor is not preserved. You cannot put, you have to put something that control the L infinity nor. And the H1 control the L infinity nor. Okay. Okay. Now you can ask, what happened to this side? Right? Well, with Frey, Linares, and Munoz, this year we proved that for the KdV, if you go to the other side, you go to the left, and you are a little bit, for any constant, if you take a power more than 1 of the log and multiply by t, and you put any constant here, you don't see anything either there. That means, okay, what is the L2 nor? Well, C0t, you have nothing here. This one, t log of 1 plus x, you don't see anything here. And depend what you want to believe, then let's put 2/3 here. Two-thirds minus, and 2/3 minus 2/3. Then all the L2 nor have to be here. And if you are in the case of the KdV, it should be only here. You don't have anything moving to the left. Okay.
So what you are integrating are the first are 2 terms of the equation, right? Or
And sorry, when you integrate what? I'm sorry.
what you are integrating, no, this is the L2 of u and the L2
Of the derivative.
of the derivative.
You can forget the derivative for the moment. I mean, to make it much. Okay. Then, of course, the resolution conjecture says something like this, that generically, for initial data corresponding to the solution of the generalized KdV, the solution eventually will result in a radiation component that disperses as a linear solution plus a localized component that behaves like soliton or multi-soliton or multi-breeders. Now we have multi-breeders. Recently,
What is a multi-soliton?
multisoliton is the addition of solitons, right? Okay, to have a multisoliton solution is to have this. Let me see. To have a multisoliton solution is that you start with this profile, right? This is t equal to 0, and prove that you have a global system.
Okay.
Okay? And if k is equal to 1 and 2, you know that they collide elastically.
And what is a multibreeder?
Well, multibreeder is a breeder that it will be multibreeder. It has proof only for k equal to 2. It's something that looks like this. And that was proved recently. And the solution is the part inside. This is the envelope. This was proved recently. I don't recall the name by heart, but this is proof that you have multibreeder for the KDV. Okay. Okay. Then we are not going to talk more about breeder. We are going to talk about much simple things. Right? Then more simple thing is that you need some decay of the initial data for the dispersive effect. The dispersive effect is coming from this part. This is the dispersive part in the KDV equation and the generalized KDV. For the dispersive effect to be felt, you need to have some decay on the data. Because suppose that you put this initial data, and this is a calculus. If you put this initial data, you have this solution. Suppose that you put plus here, then you have x1 minus t is a solution. Suppose that you put plus u of x0 equal to x, then you can prove that this is a solution. Because when you take three derivatives, you don't see anything here. Then this is a solution of this equation. That is the Burger's implicit Burger equation that blows up at t equal to 1. Then if you put data that doesn't decay, this part doesn't count. Then you have to put data that have some decay to fill the dispersive part. Okay. Then, if you take solution of the generalized KDV and you take solution of the linear part, this dispersive part, now you don't have no linear part here. They preserve the L2 norm. You multiply by u here, multiply by u, integrate by part, and suppose that you have enough decay, then you prove this. Then you prove the L2 of the linear part. And now let's try to see that decay of data is related with the smooth of the solution. Okay, let's see the simplest case. This is the operator that gives you the linear part. This operator commutes with this one. And that's a very simple computation. Therefore, suppose that you want to solve this problem, you know how to solve this problem, and you have a solution of this, and then you want to find a solution of this one that is the same data, but multiplied by x. Therefore, the solution of this, since this operator gamma that depends on t commute with this, you apply gamma here, you put it inside, and you see that the solution B that you are looking for is exactly gamma applied to U here.
Wait, what, gamma, oh, gamma is, X.
Gamma is exactly this one here.
Yes.
Then in particular, if you write gamma explicitly, now you have that, since you preserve the L2, you have that these quantities in L2. Original, you only have that X multiplied by U was in L2, but now you have that X multiplied by T, second derivative is in L2. Then when T is different than 0, you start to feel some regularity in the solution. When T is different than 0, the solution, at least locally, is in L2 because X is a function in L2 locally. If you integrate in a, then this is also locally. Then you have that, you have two derivatives local in L2. You start to feel some regularity by this commutation. Therefore, if X multiplied by U is in L2, this quantity is in L2. You feel that you gain something. Then you can prove the following. And if you go in this direction, suppose that you have the space that you have n derivatives in L2. And suppose that this you have the space when you decay like 2 to the m. And suppose to simplify our life that n and m are integers. Then if n is larger than m, then if you start with this data, you stay with this data. You describe a continuous curve when time involved in this space. Only if you have more decay, you have more regularity than decay. This parameter here, the number of derivatives is larger than this one.
Mm-hmm.
What happens if n is more? Do you have more decay? Then then you only preserve this, but this extra decay will be transferred into further regularity. If you can keep going like this, you can prove that the solution flow of all the generalized k-dV preserve locally the Schwartz class, because preserve as much regularity as much decay in that order.
Mm.
Okay, what happens if you have more decay than polynomial? Okay, then this is cut observation. Suppose that I take the linear part.
Mm-hmm.
Right? And suppose that the initial data here satisfy that this is in L2. Suppose that the exponential of beta x by u of x0 is in L2. And u, okay. Then what is the equation that B satisfies? B satisfies this equation. If you write every step in terms of B, you pass this exponential to this side, you apply your derivative here, you will see that B satisfies this.
Mm-hmm.
But who is B? Well, it's the k-dV, this term plus this term that is a translation, right? But this is that multiplication. What is this term? dt minus this. This is the heat equation. And the heat equation, you know that you gain a lot of regularity out very fast. Then that tells you that this operator, when you work with exponential decay, becomes this, and then there is a parabolic since because you have the heat equation there. In particular, you prove that if
I mean, the heat equation will be the first term.
this term, because it's
Oh, you mean the right-hand side of the heat equation.
yes, but you have this, yes, but you have the derivatives of, yes, this term with this term will give you the heat equation. Still, you have the k-dV.
With the yeah.
Then if u of x0 multiplied by exponential of b of x is L2, then Cato proved that for t positive, because now t is an issue, t has to be positive, because otherwise you will be backward parabolic. Then the solution is infinity. if you solve this, the linear part of the KdV with a data that decay exponential, the solution is infinity for T positive. By doing this trick, you just have to prove that B, you just have to prove that B is infinity, because if B is infinity, U is infinity. It's infinity. But B is infinity because the initial data of B is this, that is in L2, and you are solving this. This is parabolic, this is a group, this is a group, this is a multiplication by a number. That doesn't make any difference. Then the best result in this direction when you are not in the nonlinear case is this one. This is Tarama, and he proved the following. If you have a data that is in L2 exponential to the power 1/2 with some delta positive, then the solution of the KdV become analytic in X for any T positive, for any T different than 0. That is that's a beautiful result, because then you cannot be flat at any time. Analytic function cannot be flat, cannot have, cannot branches of infinite order, nothing, right?
But those are real solutions. So that means
Yes, real solution is real analytic.
real analytic.
The same result for this power is unknown. Why? Because he used the inverse scattering in a very strong manner. He used the inverse scattering, all the spectral scenes that are well known when for the Liouville problem related with the KdV. Then this is a totally unknown result, but this is a beautiful result. There have been proof that, for example, you can only, if you put this condition only for X positive, you will be analyticity for T positive. Okay. Okay, let's see some uniqueness results.
Just one question.
Please.
So is there a conjecture at least?
I
when
think
K is equal to 2 or 3 and
well, it should be. I think that this should be true for any power. Even if you suppose that you put the initial data, you can even put higher power here. Suppose that put a square here. Suppose I say if I have an initial data that the K Gaussian, then the solution for K equal to 2, 3 become real analytic. That will be a beautiful result. Okay, we will go in some moment to how much is the best possible decay that you can have. Okay, let's some uniqueness, and we will mix in some moment uniqueness with decay. Okay, but let's go to uniqueness. Then So and Chevre prove the following. If you have a solution, two solutions of this generalized KdV, and they agree in an open set, they have to be identical. This is kind of unique continuation, right? Then Ben-Sham proved the following. If you have a solution of the KdV that decay, that is 0 here, you have a solution of the KdV that vanishes in a semi-line here or here, doesn't matter, then it has to be 0. Okay, what is the difference? See, here you are asking for two different solutions. Then when you have for two different solutions, you are working with an equation that is satisfied by the difference of two solutions. That is a different, it's not this one, it's more complicated. But since he's using inverse scattering, he needs to work with equation. He cannot work with the difference of two, because the difference of two is the KdV. If you have two solutions of the KdV, the difference doesn't satisfy KdV. Then this result uses inverse scattering, and that's it. You cannot use two solutions. It has to be one. Then this is a result that have to do decay and uniqueness. How fast a solution of the k-dV can decay? Well, that is not a very precise question, but this is a possible answer. Then there exists a constant that depends on this k here, that if you have a solution, two solutions in the good space, and these two solutions at the time 0 and at the time 1 belongs to L2 with this weight, they are equal. In no moment you are assuming that these two solutions are equal. The only thing that you are assuming is that at 2 times they belong to this space. They belong to some L2 with a big weight. And then they are equal. That means this is stronger certainly than this one, because you are assuming that you are 0. Right? You are assuming that you are 0 in 2 lines. I'm sorry. Here you are assuming that you are 0 in 2 lines. You are assuming that you are 0 in 2 semi-lines. And here you are assuming that you have exponential decay with 3/2. And can be to the right or can be to the left. Okay, let me explain why the 3/2. If you have a solution, you consider the linear problem. Right, the solution, you can write it after taking Fourier transform. You can write that this is a convolution of the 80 function with the initial data. And the 80 functions have this asymptotic behavior. For x negative, decay to x, decay like x to the -1/4, and it decay exponential to 3/2 to the right. Then if you read this theorem, you say, well, but this is, now we have a machine. Then you look what is the decay of the fundamental solution of the linear problem, and we should have a theorem for the nonlinear one, right? Right? You go, what is the decay of the linear part? You plug it there with some constant, then you should have a theorem like this. How do you prove it? That's different, but well, look, think about that. What is the decay of the fundamental solution of the Schrodinger equation? It doesn't decay. It's the exponential of I x squared over the square root of t. It doesn't decay. Then this doesn't apply to dispersive equation. It's only applied to this one. Okay, then you can ask one question. Is this 3/2 the best possible? Even, I mean, look, if you put y sub 2 0, you are saying, if I have a solution of the k-dV, this is 0, this is 0. I have a solution of the k-dV that at 2 times decay with this power, then is 0. If I put u2 identically 0, I still have a theorem. Then what can you say if you decay like 3/2? Well, this is a result with Isasa and Linares that we prove the following. Suppose that you have a solution of the k-dV that initially is L2 and the k with this 4. Then you can prove that at a later time it decay also with this power, but this coefficient here is deteriorating with time at this source. This constant here
It's positive. AT is positive.
it is positive, but when t is equal to 1, right, this is 1. You can start with AT as big as you wish, but when t is equal to 1, this constant becomes 1. Then you don't have this theorem that at 2 times you decay with a big constant. It's a matter of constant now. Therefore, it's in that sense it's sharp. However, okay, you can think about that. You can ask, this is a solution of the k-dV. All this question makes sense for for a general one, but let's suppose that you have KdV, and suppose that with some way here, right? And you, but for a very long time, then this weight should be exponential of x1 plus epsilon. If you decay faster than the soliton, right? You cannot do that forever. You cannot do that. You can do that for a short time. You can, like this one proof. But this proof only for one side, for T positive, right? Then you can ask the question, can I have a decay stronger than the soliton to infinite number of T, even with translation? Okay, remember that you have to translate things. Maybe this is x Tn 1 plus epsilon, something that you go with a soliton. Then do that imply that you are zero? This is a different, this is a result at infinity. That is more interesting, in my opinion. Okay, then one last thing that I will say, and it will take me 5 minutes. Then if you put all this decay together, right, you can prove strange things. And let me give you something that is not so complicated to prove and is quite interesting. Is suppose that you write the solution of the linear problem is given by convolution with the 80 function. This is convolution with, and I don't remember, is 80 function x. Okay. Then, if you use the Hammer principle, you can write the solution of this equation using the group of the linear problem. This is like the, in ODE, like, how you call that in ODE, variation of parameter?
Yeah, variation of parameters. Yeah.
Okay, you can prove that if you put a lot of decay, this nonlinear part have more regularity than the linear part. Right? In fact, you can make a general statement, but let's not move in that direction. Then you can prove that this nonlinear part, and then the solution of the linear part you can control. For example, you can, for example, let's do this. You can do this with the linear part by itself. You can put any data that you want here. And if the solution of the linear part here is regular, then you can add something that is make irregular here, and then such that when you solve it here, is regular. Then the irregularity of this is not affected. The irregularity of this doesn't affect this. The irregularity of this doesn't affect this, because the decay, you have gain. Then if you put this together, you can prove the following result. And this is the last thing I will mention. That for the KdV, Bond and So prove the following. You can put a collection of time that doesn't have an accumulation point, and they are not at the same time. You can, between minus T and T. Then you can put, they don't have a, okay. If you want to put finitely many, then you can construct a solution of the KdV that is C3 in all these points, everything here, except in this point when you are not C1. And then you're going to say, how do you know that you have a solution? Well, you have to understand the solution as the solution of the integral equation. And then you don't need to be C1. That's okay. Then you can have a solution that is very nice everywhere here, but it have this corner in this point. You have corner like this in all these points. Then you have a wave, you have a corner disappear, it reappear here. You have a corner, it appear here, disappear, reappear here, and so forth. Right? This is what they call dispersive blow-up. Okay, I think that this is all that I want to say. Thank you for your attention.
Wow. Any question or comment?
Well, I mean, Wilfredo was complaining because I didn't put too many introductory video, but he said that he will have some.
There is one there. Why don't you show the video? That is a nice video.
Okay, I'm going to show. Yeah, but that is the video of the elastic collision. Okay, let's see. I have to say why I didn't put the more video is because I don't know how to remove the commercial of the video.
Yeah.
I want to, okay. This is a elastic collision of the KdV. There is also one for the breather that you can see that the breather can move to the right, can move to the left, but they have a commercial, and I don't know how to remove the commercial, and it bothered me to put something with commercial. And there is another one when they have the experiment of Scott Russell in a lab, and that is beautiful because when I was in Penn State University, they did that experiment, right?
Which one? Which one? Sorry.
The same experiment, this one that you create one traveling wave.
Oh, okay.
And then you have this is in plastic, transparent plastic, and you can that, and then they can do numerical experiment. I mean, to solve it numerically and then superpose the solution to see.
At the Science and Industry Museum, they have a channel like that one, and you can see the wave there. Yeah. Okay, thank you very much.
Thank you. Thank you for the invitation.
So, well, at least now I know what a soliton is.
Well, but soliton is only if the power is 2 and 3.
Yeah. And I was really impressed with those explicit solutions. That to obtain that has to be hell, right? To get it.
I don't know how Watabi deduce that. Okay, this is
because most of the time, I mean, for instance, I remember the Carlos Koenig talk, I mean, and your talks, the one that are always estimate and, you know, stability, whether it's not, the solution is stable, it doesn't blow up and things like that. But I think it's the first time that I see an explicit solution in this type of problem, right? Those are not frequent, right?
Well, I mean, it seems that when you are in the integrable case that you can compute sin explicitly, and by strange reason, the hyperbolic secant always appear, right? Because the hyperbolic secant is the solution of this elliptic problem. This one. This problem is very close to the one that we solve with this for the traveling wave. This problem is the one that we solve for the traveling wave if alpha minus 1 is equal to k. Then you don't have to put positivity because, right? You're looking for something positive, right? This is hyperbolic secant, and these appear in many, many problems, right? This is the elliptic problem that is behind all that.
Probably this is a, it shouldn't ask you that. But for instance, some of the KdV, K equal 1, the insight that has been obtained since this guy saw it the first time, and all the description and solution, does that has for, technical application in hydraulic or something like that? Do you know about?
The KdV have a lot of applications, even, as I say, as the evolution of curve that the filament, for example, a lot of appear in the evolution of, you have a curve that is the center of a vortex. It's a vortex curve. This curve is making everything to rotate around. And of course, you rotate in a plane that is perpendicular to you. Right? And in what direction this move? Well, it come out that if you have a curve like this, then this is the tangent and this is the normal, and you move in the direction of the binormal. Right? Then if you have a family of curves that satisfies some property, then it came out that you can prove that these curves satisfy the modified KdV in some sense.
Oh, wow.
And it's even go to this, and what I would say it's almost true. If this curve, to recover this curve, you need the curvature and the torsion. And suppose the curvature is this, and the torsion is, the curvature, I don't know how to write the curvature, okay, T. No, this is.
No, capital T or whatever. Well,
okay.
Curvature is usually K, right? And torsion
Okay.
is R, right? Yes.
Then if you write this, that is a complex function. These complex functions evolve accordingly to the cubic Schrodinger equation. Almost true, but there is a correction here. Then you have a curve that is a center of vorticity. Then you can prove that this curve that depends of the parameter s and the time, it evolved like this. The derivatives of this is in the direction of the binormal. Okay, no, let me write it in a better way. Okay, this is your curve. Then you have dt of x is ds of x. Cross product with this. Then you move in the direction of the binormal. Right? That is, this is a speculation, but this is the way that smokes border rings move, right? You have a ring and they move. Then if you call this x, sorry, to recover x, you only need to know this. Put x equal to x. Okay? To recover x, you need to know the curvature and the torsion. The way that this equation transforms is exactly this equation transform this quantity.
Okay.
there are a lot of relation between vorticity and Schrödinger and cubic modified KdV.
Okay, we need to stop here. Thank you very much, Gustavo, again. Thank you for your time, and I hope that everybody that has been here has obtained some ideas. And thank you for coming. And well, I will post the links as soon as I get it from Zoom. Okay, thank you again, Gustavo.
No, thank you. Thank you for the attention, guys.
Okay,
Thank you.
bye.
Bye-bye.